we're streaming. Let's check stream health. Looks good. Okay, this is where we left off. We left off at using location. And I am going to repopulate a few things. So I'm going to the pandas tab, and I'm going to look for read CSV. Is it read? Do you know if it's underscore CSV? I bet it is. There it is. Right, so this was the data frame we're working with, so I'm going to get that again. Oh, did it not work? Oh, I don't have pandas. There we go. So I got my periodic table back, and that wasn't too bad. So this periodic table is actually going to be missing some of the transforms we made to it, so we'll have to work with that. For example, this doesn't have the number of outermost electrons, right? So we could add that. We can also use number of valence as a proxy. But this should be enough to go forward and start using location. So here's something that I thought was interesting about the periodic table. When I was like reading little fantasy books about like wizards and stuff as a little kid, everyone was really into whether things were metals or not, right? There was always the metal that comes from the heart of a fallen star and all that stuff. And I never actually had a strong sense of what metal meant, right? Growing up, I think you kind of know iron is a metal, and then like maybe you've heard of copper, right? But there's all this other stuff too. So apparently calcium is a metal, right? I don't think of it that way, right? I think of it as a vitamin, right? But it is. And then I think titanium and chromium are very straightforward, right? But let's take a look at some of the rows of this periodic table and see if they're metals or not. So I'm going to take my data frame, and I'm going to look at the integer locations in the data frame. What am I going to look at? Well, I could look at some range, so we can just look at the first 10, right? We can't actually see on here on this screen right now if any of these things are metal. So what we're going to do is df iloc 10, that's part of a data frame. We're going to take a smaller part of a data frame. I'm going to do an index, but that index is going to be the list of two names, the element and whether it is a metal or not. And then I'm going to make sure I close that. I had two open brackets, so I have two closed brackets, right? And go ahead and hit enter. Well, lithium's a metal. Lithium and lithium-ion batteries, for example. Beryllium is also a metal, and I think of beryllium as being the thing that gives emeralds its color, which kind of makes sense because I think iron gives the red color to rubies, so perhaps it is metals that cause gemstones to be colored. We can look at some other, sequences. We can look at every 20th, which we've done in the past. From this, it looks like many of the elements are metals, right? The only one that's not is hydrogen, but scandium, niobium, promethium, thallium, and mendelevium are all classified as metals, right? It looks like the two options for metal are not a number, NaN, and yes. I would have probably expected true false personally, but that's how this data frame is implemented. So, what is NaN? Well, I'm going to go ahead and import NumPy again. We were working with that as well earlier. Because I want to use NumPy's square root, right? I think if I do this, that just seems wrong, right? Look at that. Python thinks the square root of -1 is -1. Do you see that? Because this is how you compute the square root, right?
-1?
Yeah. So I typed -1, raised it to the 1/2 power. Is it better if I do this? It's just wrong. It's rounding? Interesting. Well, anyways, I didn't really expect to see that. So anyways, that's why we're going to use NumPy square root, because it's actually correct. So we'll take NumPy square root of -1. And we will see that it is not a number, and we'll also get a warning that maybe we should have been a little careful about doing that, right? That's basically what not a number means, right? I think Maybe if I divide 0 by 0. Yeah, that's not allowed. Historically, 0 divided by 0 has been not a number, but I guess they don't allow you to divide anything by 0, so fair enough. I don't really love the notion of using not a number to represent no. This is probably the one thing about pandas I don't like, and that's why it's the only polars shout out in here, polars being the competing data frame. I can't really do anything about it. The things other than metals are also broken into two groups. And we can take a look at this by looking at elements 12 through 15, which we're going to do right now. Where was it? There we go. Let's look at 12 through 15. Element metal. Oh, 12 through 16. So aluminum, I think that's something I think of as a metal. That's the metal they use to make airplanes, right? Silicon, I think, as the thing they use to make semiconductors, so like CPUs. Phosphorus and sulfur, I think of them as things in a hot springs, right? Not necessarily a metal or anything like that. And so we can look at two other columns here. We can look at the non-metal column, and we can look at the metalloid column. I'm not used to hearing the term metalloid too much outside of chemistry classrooms. I think it's a pretty technical term, and I don't know that it's caught on. My sense is also that there's some metalloids that people don't all agree if they're metals, metalloids, or non-metals, right? There seems to be a gradient of metalness, right? But this is just a quick example here of a way that we have three different columns representing whether something is a metal, a non-metal, or a metalloid, right? Silicon being a metalloid to me makes sense because we call it a semiconductor. We don't call it an insulator. It's not like concrete. We don't call it a conductor. It's not like copper, right? It's something else, and that's why it's used to make semiconductors, right? So I stylized this as non-metalloid, which I thought was a fun title for a slide. I take great pride in that. So I am going to do some data frame manipulation here, right? And before we get too far into that, I'm going to let you know what my goal is, right? I'm looking at metal, non-metal, and metalloid, and that looks like three columns that all say how metallic something is. So I'm going to try and create a new column that says how metallic something is, and then get rid of those other three columns. So I'm going to create a column called metallic, and I would do that by saying, oops, oh, did I press F? Is that? There was some keybind I pressed there I haven't pressed before that caused this to full screen, because I usually do F11. But I didn't have my hand up there. Oh, yes, it is F. Okay. On your computer, if you're on the slides and they're not full screen, if you press F, do they become full screen?
Yeah.
Okay. Good to know. So, we're going to go ahead and introduce a variety of things. So the first is, I can say df metallic. Okay. That would be a new index in our columns, right? There's nothing called metallic, so we could add that, right? But I'm also going to show how I'm going to add it, and I'm going to introduce np.where. So this is a NumPy thing that we're going to use within pandas. And what's it going to do? Where is going to say where something is true. So it's going to give me back a series of row indices where something is true. So I can make an example here. Let's look at np.where of df metal. And that gives me everything, because every single one of the data frames has or every one of the rows has something in that column. So what I need is actually something a little bit different. I'm going to see np where df metal equals yes. And then that's going to be the names of my metals. But I can provide additional arguments to np.where. And you'll see, oh yeah, we interesting. This is quite a bit shorter, right? So hydrogen, helium are gone. Many things, everything from 3 to 10 is gone, right? I can say sort of whatever I want for np.where. So I can get a series of 1s and 0s that represent whether something's a metal, or most properly, I can say it is a metal or it is a non-metal. And there I have the list of whether things are metals or non-metals. So by putting that together, then I'm able to say df metallic equals np. I'm just going to type it again. I shouldn't be typing twice, but here we are. Metal. Yes. Right. So this is saying, give me all the things that have metal says yes. And if they do say metal yes, then call them metal. And if they say metal no, call them non-metal. This is also about what the favorite music genre of each of these elements are. We got a bunch of huge metal heads on the periodic table. They really like Metallica. You a big Metallica fan?
No.
Okay, we'll work on you. I think we can get you there. Okay.
Yeah, really.
So, we did it. Let's take a look. A silly thing about Python, and I'll probably never get used to this. I guess a lot of languages are like this. A lot of times when you type something in, there's not a problem. It doesn't show you anything, so you only get error messages. But that looks great to me. Oh, let's look at some elements too. Element, metallic, boom, and maybe we'll look at some subset of them. Nope. There we go. Sodium's a metal. Scandium's a metal. Gallium's a metal. I've heard of that one. Niobium, heard of that one. Antimony's not. Promethium, we know. Yeah. What happens if we look at this by 12? Do we get some things we've maybe heard of before? Rubidium. Oh, manganese. Manganese. That seems like a recognizable metal, right? So that's cool that that's metallic. Associate. I don't know what that is, so it makes sense that that's a non-metal, right? So this is just something we've added to our table. There's one problem with this column, and it's not a huge problem, but it's a bit annoying, which is that this only lists metal or non-metal, and it also says non-mtal instead of metal, so I should probably fix that real quick. Hold on. Okay, we fixed it. I need to also put all the metal weights in here, right? Oh, and I should verify that these are metals and non-metals. Make sure I did this right. Non-metal, yes, non-metal. Non-metal, yes, non-metal. But really, probably what I should be looking at here is, should be looking at the data frame, np.where, df metalloid is yes. Oop. There we go. Oh, and I didn't put yes in quotes, right? There we go. So that's a little bit too hard to get to work here, I think, right? Oh, well, we tried. Oh, maybe I just have to do df.log. There we go. Okay, so here's the metalloids. All of the metalloids. Let's just look at, for them, element, whether they're a metalloid, just to confirm, and whether they're metallic. So all of these are misclassified, because they should all say metalloid instead of non-metallic, and that's unsurprising because here I don't actually deal with the case where anything's a metalloid. I just check to see if something's a metal, and if it's not, I say it's a non-metal, right? So boron, poor silicon. We talk so much about silicon. We would have no jobs without silicon, right? We're all hoping to work in the silicon industry someday, right? Germanium, arsenic. It's not very good for you. Try not to eat any of that. And by the way, there's not very many metalloids. I think there's 7 of those. Did I count that correctly? No, maybe, yeah, 7. So we're not dealing with too many of these things, right? But you know, for each of these, we should do something nice. and that's label them as metalloids instead of nonmetals. And I think we can go ahead and do that. Let's see if we can. Is that how you spell metalloid? Yeah. Uh-oh. I got a warning. So we should be careful about how we're doing that. And the most important thing, I think, to be careful about how we're doing that is, if we ever see one of these warnings that directs us to the documentation, we should stop what we're doing. So let's take a look at this. We want to say, oh, right, I think we already did all that. What's going on here is that these are different data frames. They're not the same thing. And I think I can do a different example here without the np.where, right? And apparently that's allowed, right? But if I go ahead and take df, and then we look at, well, let's just take a look at this. That doesn't actually change anything. So I'm going to show you what I did again. I take the data frame. I look at all of the elements of the data frame where metalloid is metallic. I take the metallic value and I set it to metalloid, right? And so that should be exactly these elements. And it doesn't work, right? It doesn't work. The reason for that is that this is creating a new data frame. That's not changing df, right? So df is some data frame that exists out in the world. I take a new subset of that data frame. That's what this means by copies and slices, right? There's just different words for these. It's just a different data frame. So we're going to have to use something else. And the recommended way to use that, and this is correct, is to use loc. I think of loc and iloc as cousins. And so they're not going to be too different. And we're just going to change it right here. I'm going to say .loc. Now, what is the difference between this? I just typed those 4 little characters, but what does that mean? This is no longer creating a new data frame using this sort of column notation. Now, this is doing something within the existing data frames. This is the same thing as changing df.columns or df.shape or df.index or something like that, right? Because it's the dot. And that doesn't work either, I think. So, what are we going to do? We're going to have to use this sort of indexing here, right? Even when, let's go back here. What's going on here? Well, I have loc, right? But that means that this is still the same data frame. But as soon as I look at a column of the data frame, I'm looking at a different thing. And actually, a very easy way to do this is to say, we're going to have something, I'm going to call a variable temp. Temp is just the list of nonmetals, right? And so if I update temp metallic to equal metalloid, that doesn't work even, right? But I think what I can do that just gives me metalloid, right? So none of this stuff is actually altering the underlying data frame. But when we're working with the NumPy arrays, I stressed that when we're dealing with slices of things, when we're dealing with multiple parts of the array, we need to put them in the same sort of coordinate system. So let's go ahead and do that. And I think I can just, is it as easy as this? Oh, I didn't mean to do temp. Okay. And then let's check the df metalloids. Where are they? And now they're all changed. So what's the core insight here? Use this. I wanted to look at everything where metalloid is true, So that's part of the data frame. And then I wanted to look at the column metallic. So these are rows. Those are all the metalloid rows, boron, silicon, germanium. This is the metallic column. So this is the combination of all the rows and the columns that are the metallic attribute of the metalloids. I don't want to set all of the metallics to metalloid. I don't want to set all of the elements to metalloid, right? So I have to take this subset by doing this. And I think it works great. I wonder if even... But that one's not allowed, yeah. So you have to use loc, and you have to use loc with commas. Let's just try one other thing. I don't know. Symbol equals H. That's hydrogen. And then we'll look at its element. Probably has to be in commas, or in quotes. That one doesn't work. But I think if we do loc... Oh, that's not allowed either. Okay. We tried. Oh, I see what I'm doing. Sorry. It's df symbol. This will get just hydrogen. And that will not get just hydrogen. That is something else, right? So this is the benefit of using loc. When we use loc, we get to use the comma coordinate notation. And I think that's really cool. The thing with these data frames, right, is they seem so squirrely under the hood, and then you realize what would happen if you were allowed to do changes like that, and it's like, oh, well, you'd never be able to look at a single column without accidentally changing what's written in it, right? So, let's look at our df iloc 12, 16. Sorry, I really always want to do regular brackets for iloc, but you have to do the square brackets, which is not something I like, but it doesn't make sense to complain about it. Element. Metal. Non-metal. Metalloid. And metallic. I was going to make a joke about typing Metallica by accident, and then instead of making that joke, I said, no, I'm not going to do it, and then still had a typo. There we go. And I think this is exactly what we want to see. Aluminum is a metal. It's listed as a metal and metallic. Silicon is a metalloid. It's listed as metallic metalloid. Phosphorus and sulfur are nonmetals, and they are listed as nonmetals. And that seems cool to me. One of the benefits of this is, you remember we were plotting things at the end of yesterday? Well, now it's a lot easier for me to plot metals, metalloids, and nonmetals, right? Because now they're all in the one column. So I just say color based on this column. And in fact, I can do that. Import matplotlib dot pyplot as plt. plt dot plot, and what am I going to plot? I'm going to plot the atomic number. What should I plot it against? Something in the y space. You like boiling point, melting point? Yeah. I feel like melting point is cooler than boiling point. Get it? Because you have to melt before you can boil, so it's necessarily cooler. It's lower temperature. Yeah. I think. df dot metallic. Maybe that's all correct. My closing parens didn't match my opening parens. We all make mistakes, and the mistake I made is I didn't put a square bracket here. Value error. Object isn't, well, oh, maybe they have to be numbers. What a shame. What if I can do pie chart? df metallic. How does that work? Couldn't convert a string to a float. Wow, nothing works. Okay, never mind. Maybe I can't plot this. I thought I'd be able to plot this. And I don't care enough to figure out how to plot it. So unfortunately, we'll just never know. You can figure it out as an exercise if you'd like. Oh, we should do one other thing. We put all this work in to have these 3 columns we can get rid of, but we still have them. Where are we? Metal, non-metal, metalloid, metallic. Too much stuff. Now I could df dot drop columns equal metal, non-metal, metalloid. I can do this. Oh, close the run. And I successfully dropped the columns, and it's showing me the data frame. But usually when it shows me the data frame, that doesn't mean I did the thing I wanted to do. And check this out, df.columns. They're still there. So what I have to do is I have to update the data frame to have the drop. So I'm going to say df equals the data frame drop. So I'm going to drop the data frame again, drop the columns, but I'm going to say this is now my new data frame. And this one does not have metal. See, it was under symbol and number of electrons, symbol, number of electrons. That just says type now, and type is the first thing that came after metal. So I did successfully drop it. You can also check by doing df.shape. And see, we're down to 26 columns. I wonder what specific heat is. Let's take a look. See that? Specific heat. Huh. Wow, it's really high for hydrogen. Hydrogen's the maximum. Okay, I don't know what specific heat is, but that's a very high number for hydrogen. What's the mean? Yeah, usually it's less than 1. Look how fast it's going down. That's great. Okay, cool. Groups. I don't know if this will impact you. I find groups a tough subject to talk about because of the word group. I sort of was kind of excited about doing this periodic table example because there's something called groups on the periodic table. There's also something called groups in pandas, not in Python generally. And then, unfortunately, and this impacts computer science education most specifically, not necessarily scientific computing, there's also group theory in mathematics. And those are the sets of numbers that have multiplication defined on them. And there's a series of additional things. What this means is there's no great linguistics way to refer to any of these concepts. So I'm going to try and refer to pandas group by. I'm going to try to refer to table groups, and I'm not going to be talking about the other group, which is the group I usually talk about. So the slide heading says groups, and it's just a mess. This is not the group we're talking about. We're not talking about a set together with a binary operation satisfying certain algebraic conditions. We're not doing that. We're talking about this one a little bit. A group, also known as a family, is a column of the elements in the periodic table. They're just columns. But they're columns in the periodic table, and we're also using columns to refer to columns in our data frame, right? We're just in big trouble here, right? So there we go. And then we got pandas, and we all love pandas. In pandas, a group by operation involves some combination of splitting the object, by which they mean data frame. So we're going to take our data frame, we're going to look at parts of the data frame, we're going to apply a function to the parts of the data frame, and then we're going to combine the results when we're done. So this can be used to group large amounts of data and compute operations on those groups. So let's take a look. Let's take a look at our groups. df.iloc. Did I start it? There's a 6 there. Oh, because I'm stopping at 60. Okay. 10. Element. Group. Here's some elements of the group. Noteworthy thing to take away. Hydrogen is group 1, sodium is group 1, and they're both in the first row of the periodic table. If we recall that, if we don't recall that, scandium isn't that far over. I think we can start it 1 and go by 8 or something. This will tell us some interesting things. So this allows us to see both helium, or all three of helium, neon, and argon are all in the same group. Those are all the noble gases together, right? So that's interesting. Iron's right in the middle. Selenium's pretty far over, right? So there we can see all of the expected details, right? So how many groups do we have? Well, let's take a look. df dot group by. I'm going to group by group. And before I do that, actually, I'm going to group by metallic, because I felt bad I didn't get to use metallic earlier. And I'm going to count those up. And this is pretty cool. We have 92 metals, 7 metalloids, and 19 nonmetals. Interesting. And I do that to emphasize you don't have to have a column named group here to type this in. This is not a Calvin-Deutsch bind scenario with the change directory command. So we have group 1 and group 18 have 7 elements. Group 2 and 13 through 17 have 6 elements. And then 3 through 12 have 4 elements. And that's actually perhaps going to remind us of what the shape of the periodic table is. I think this one I can plot. Can I make a histogram of this? Oh, it made much larger bins than I was expecting. See, I thought it was going to do the other direction. Does that make sense? So this is... What is this showing, right? This is showing how many 6s, 7s, and 4s there are, I think. Right? So there's a bunch of 4s, a bunch of 6s, and a bunch of 7s. Oh, maybe I guess I want a. Is there a bar chart? I don't think there is. Height. Oh, I think I can do this. I think I can do df.group by group count. Maybe I can just do this. Does that even work? No. Let's see. So height equals group by group count. I don't really know what I'm doing here, but it seems interesting. Atomic number. Yeah, okay. I don't know how to make bar charts. Should we look it up? Do you want to make a bar chart? Let's figure it out. Matplotlib bar chart. Pyplot bar. Okay, so I need an x and a height. Okay, and so that is going to be, x is going to be floater array, right? And then height is going to be floater array. Okay, we can do this. Okay, so I have, I'm going to do something, what am I going to call it? We're going to call groups equals df.group by group dot count. Okay. And I'm even going to just get atomic number. It doesn't matter if it's atomic number, I'm just taking one of the columns to get the counts, because it's counting in every column. Okay, so this is groups. Okay, and so I'm going to say x equals groups. Groups group? Is that what it is? Groups group. Oh, it's just in a range, right? It's in a range from 1 to 18. Okay. And so if we do groups atomic number, that's fine. Really? What's it called? What are the columns of groups? Oh, groups doesn't have columns. Okay, so I'm going to do plt.bar, right? It's called bar, right? I'm going to do an np.arrange from 1 to 19, and then I'm going to do groups. There we go. So what did I do? np, let's, okay. So, np.arrange 1 to 19 is the numbers 1 through 18. Those numbers 1 to 18 are the same as the columns. I wonder if it's like, or groups.index. I could have done that instead. Okay, so let's try that. Where did I plot it? Okay, so I can do plt.bar. On the x-axis of my bar chart, the thing I want is the index of my groups. So I'm going to say group, which is the name of this data frame, dot index, okay? And then on the other side, I just want the values in groups, so I'm just going to put groups there. And then I'm going to plt.savefig bar.svg. Oh, and it changed this one too. That's very cool.
I tried it and I forgot. I didn't add savefig, so it stuck again.
Oh, okay. Yeah, you can always just close it and start over. I don't know what else to tell you. Import os.system, open bar.svg. There it is. Look, I got two of them. It's the same thing, but I didn't do twice as much work. Wow. It looks like the periodic table.
Yeah, it does look the same.
Yep. Right? Same shape? Same shape. I should probably add this to, wow, look at that. This has mouse over. How did they get that to work? Does that happen on Wikipedia? This one doesn't have mouse over. This is some like really slick HTML thing, I think. Oh, here's all the atomic orbitals we dealt with. Remember when we visualized these ones? Or I did that one, right? 3D. We made that yesterday. Okay. Cool, we did it. So I think something I need to do is what I'm realizing, is that I should come over to here, and I should also add an appendix that has all of the data sets we use in it. So it should have the income tax, and it should have a picture of the periodic table, because I wanted to pull up a picture of the periodic table there, and I didn't have one on the course website. Very good. Let's look at the mean of the melting points. Okay. df.group by group. That one's in these brackets, because it's an argument to a function. This one's a melting point, because we're looking up something by an index. Does it really make a difference in pandas? Kind of no. So here are all of the melting points by group. And you know what I bet we can do? I bet I can call this thing groups. And I bet I can make a new bar chart. And I bet I can save that bar chart as plot.savefigbar. And I bet I can open that bar chart with openbar.svg, and look at that. It's the boiling points by group. So things closer to the middle of the periodic table are more solid at room temperature, and things lower in the periodic table are less solid at room temperature. There's something pretty interesting going on here at 14. I don't know what's going on in group 14, but that's kind of interesting. Here I just plotted it as a naive plot. So this is the same shape as the bar chart, right? I just used dot plot. And let me show you that example. PLT or groups dot plot. Okay. There it is. Just added it to the plot. Ooh, I'm gonna take a bite of breakfast. Alright. I think group I is one of the two most interesting things in pandas. I don't know how often other people use it. I use it all the time. I pretty regularly have some data that I care how I want to use it, right? And so, I study computer hardware, so I took all these measurements over this type of hardware and this type of hardware and this type of hardware. Throw it all in the same data frame, just group by when I get it back. I like it. Let's do some merges. So, the motivating example here, I'm going to use the example of some of these elements seem to have weird names. I don't know that we've seen any of them yet that look that weird. Well, let's take a look. df. Let's look at name. Let's look at symbol. Are we going to get any ones just here? It's not name. It's element. Alright, so hydrogen starts with H, and its symbol starts with H. Helium, lithium, beryllium, boron, fluorium. Right, so all of these seem pretty reasonable to me. Is that still reasonable if I start looking at subsets? It's like, yeah, it still looks pretty good. Then we get a weird one right here. Potassium does not start with K. It's not the first letter of potassium. But all of these other symbols look like you just take some of the letters from the element. Take maybe the first two or the first and the third, right? This one takes the first and the fourth. That's a little bit spicy, right? But this one just has a K in it. That's real odd, right? And so I thought that was worth looking into. And so you can do a variety of interesting things like this. So for example, I can take df.iloc 0. This is hydrogen. I can look at its element, which is hydrogen, and I can look at the first letter of hydrogen. I can do the same thing with symbol. And I can check that those two things are equal to each other. Does not support item assignment. I have to use double equals to check the three. Okay. So these are true. And it's also true for 1. And then it's not true for potassium, which is 18. So I think we should do something about that. And my proposal is we look into it, we do a little bit of research, and we figure out what's going on. Here's the example with gold. Ooh. My toast is exploding, look at that. There's little pieces everywhere. See, different. So, We can write a function that checks if two things start with the same letter. Isn't it too bad? And then we can say differ. Just going to get these back. And I can see that those two letters differ, right? And I can also see that they don't for helium. Okay. Cool. What can I do from there? Well, let's go ahead and vectorize differ, and then we can apply it to data frames. I think what's going on here is I don't think I can say differ of df element and df symbol, right? Oh, it just says they're true. That's funny, because I think df element is this thing, and then if you take 0 of it, you get hydrogen. So it's saying that hydrogen and H are not the same value, right? So that's not exactly what we want to look for. We want to really have np.where df.element and df.symbol differ. And view.where differ df element df symbol. And so that's not really going to do anything we want it to do yet. So somehow we need to get it so that we can apply differ to every single one of the rows in this column. And that's what mp.vectorize is for. We've got to mp.vectorize differ. Okay? That's still not going to work. So what are we going to do? Well, let's just take a look at the different vectors, right? So, oh, because I said differ instead of diff-v. Okay. And this is basically the same thing I'm doing right here, right? I'm vectorizing difference. These are the elements where the element and the symbol differ. These are the elements where the element and the symbol differ. And I can just say df of this. Oh, is that not allowed? How close was I? Can I just say? Oh, I don't even need np.where, do I? I can just do this. Yeah, there it is. Okay. And let's only look at the elements. So there they are. Sodium, potassium. Oh, let's look at the symbols too. This is pointless to just look at the elements because we already know. Okay. So sodium is Na, potassium is Ka, iron is Fe, silver is Ag, tin is Sn, antimony is Sb, gold is Ah, mercury is Hug, and lead is peanut butter. And that's because they're both heavy and thick. So that one makes sense, right? What's going on here? I didn't actually know the history behind this. I knew some of them, but apparently. And I don't know why I would believe this website, but I didn't know where else to go. Some of the elements in the English language periodic table were placed on the English language periodic table before, or were established by like alchemists or something, and being referred to by an older Latin name. So English speakers, many of them, or like the areas where English is spoken now historically spoke Latin, I guess is the way to say it. And so the scientists continue to speak Latin much longer than the normal people. But the normal people are in charge of what words we use, right? Because they have more votes. So they just decide what words to use, right? So they start referring to iron as iron. The scientists continue to refer to it as ferrum. And maybe these two people don't interact with each other or something, right? I think this is very similar to the conversation we just had about what does group mean, right? I think if I ask someone on the street what group means, they're probably thinking of like a music group, right? Like NSYNC is a group. BTS as a group. Sorry, I'm showing my age there. I know we all like K-pop now instead of boy bands, but so I think it's completely reasonable that people are like referring to different things by different names, right? But when someone sat down to write down the periodic table, they said, well, we should refer to iron as Fe for ferrum because that's what I call iron. But no one else calls it that, right? Natrium, calcium are the same. Some of these are not too bad. I think argent is still in use a little bit as a color. Sometimes people will say argent. Wolfram, I guess, is still used quite a bit, and I thought it was commonly used in Europe until quite recently. And arum I'm familiar with. I've heard gold referred to as arum. Usually these refer to the color. So both arum and argent refer to the color, I think, oftentimes. But they're definitely not as common as the other words. Like usually when people say gold, they mean gold, right? So, what are we going to do about this? Not to worry, I have an ingenious plan. You're going to love this plan. We're going to do something with data frames. I bet you didn't see that coming, that we were going to do a data frame thing with this. So, let's make another data frame. I helpfully wrote this down for all of you. This was a lot of labor for me, so I hope you appreciate this. This is called names. There you go. Names. Boom. Names. There it is. Look at it. What's the type of names, by the way? Oh, no, it's just a Python list. Okay. Not to worry, I have a plan. I have an ingenious plan. I'm going to type PD for pandas, and I'm going to type dot, the same way I would with numpy.array. And I'm going to type data frame, and I'm going to capitalize it, which I didn't necessarily think I was going to have to do that. And then I'm going to type names. And by golly, it turns it into a pandas data frame just like that. And I'm going to call this data frame AD, which stands for, it was very hard to translate data frame into Latin. So this is, artis is like, I think, the frame of a house, and datus is like a date. Like a date. So this is not Latin for data frame, but this was as close as I could get. Apparently, the ancient Romans did not use the pandas library, which was shocking to me. I assumed that's how they administered their provinces, right? So, we got 80. And here it is. This is what it looks like. We're going to use columns to change how we refer to these things. Let me show you why. I don't actually know how to look at columns of the data frame, right? Or no, it's AD. It's a little weird. Look at AD again. We need our columns. Element. Gotta be a list. Element. Latin. Very good. Cool. We did it. Congratulations to us. How am I going to add this to my other data frame? This one's big and it's got a bunch of other stuff in it. What am I going to do? Well, no worries. I have a plan. I'm going to simply type df dot merge AD. And just like that, we got all of this additional information about my data frame. Figured out which ones are metalloids, and I think that's really cool. There might be one problem here, and I don't know how much this might or might not bother anyone else. Say you wanted to add the Latin names to the original data frame. That didn't do that. This got rid of most of the data, right? And I think the same thing is true if we merge in the other direction, right? That just changed the order of the columns. So the problem is, merge is taking the subset of the elements that are in both AD and DF. It's only taking the ones in the middle, right? And that might not be what you want to do, even though that's really cool. So we no longer know the name of hydrogen, right? There is a way to fix this with merge, but my impression is I should not teach you how to fix it with merge. I should teach you how to fix it with join. So we're going to do joins now. I'm more accustomed to seeing joins. I think joins are in general more powerful. They might be a little bit more of a hassle to use. We're going to step through the process with a join, and then I think that'll take us to our first exercise. In my experience, merges never work. They always do something that might be what I mean, right? But they never do what I actually mean. Like, I thought it was very clear that what I meant here was take all these Latin names and throw them in the original table, right? That's what I was thinking would happen, right? I understand why it didn't happen, right? That's not really the merge, right? But I was kind of hoping that would happen, right? So I'm going to make sure that this happens by doing joins. To do this, I'm going to create 2 smaller data frames, and the reason for that is this one's just too big to work with. So we're going to take the metalloids and we're going to take the ADs, right? So we're going to take metalloids, which are the data frame where metallic is equal to metalloid. Let's look at the metalloids. There they are. I think that's a great looking data frame. I think it should be very proud of itself. And then we're going to take the Latin name data frame, which is going to be the merge. And let's take a look at the Latin names. Very good. And something that pops out to me here that I think is pretty useful, there is in fact one metalloid with a Latin name, right? So there will be some overlap between these two things. So, I think I can merge these things. Well, I basically already did merge them. And that's not really going to accomplish that much. Well, actually, let's take a look at Latin name dot merge metalloid. Or yes, metalloids, right? So I can do the merge, but I only get this one element back, right? I only get one thing, and that's not what I want. So in order to do a join, I have to be a little bit more specific, and this join is going to want to work on indexes. There's a little bit of a problem here, which is that the metalloids index and the Latin name index don't line up. They both contain a 4, which is tin for the Latin names, and is is boron for the metalloids. And that's not good that 2 different elements have the same name. So what I'm going to do is I'm going to update and I'm going to change what the index is. Both of these data frames helpfully have elemental symbols. Elemental symbols are tightly tied to what elements are. I could just as easily use atomic numbers, right? But I want to show an example of an index that isn't numerical. So I'm going to update the index of metalloids, which is currently, again, 4, 13, 31. And I'm going to set it equal to metalloids symbols. And I said plural symbols, but I meant singular symbol. Now I'm going to do the same thing with Latin name. I put some amount of effort into making sure these 2 variables were the same length, so things lined up easier. Maybe that doesn't matter to anyone. Metalloids, Latin name. So how does this look different? The real difference is, originally I had these 0, 1, 2, 3 on the side of my data frame. That's now been replaced. The column headers are moved up one sort of text row. So they're sitting a little bit higher, and under the column headers, there's something called symbol. That symbol is referring to the index, and these indices line up. So SB antimony and SB antimony are now the same in both data frames, whereas previously we had a 4 that was attaching boron to something else, tin. And boron and tin are different things. So before I do a join, I usually make sure there is some index in common. That's my preferred way to work with joins. There's other ways to work with joins, but that's my preferred way to work with them. So, let's just look at a few columns. We're going to take metalloids, and I'm going to look at metalloids. This is just a convenience. This is just to make it easier to look at. That's all I'm doing here. Atomic number. And what I do, metallic. Very good. Metallic. And then I'm going to do Latin name. I'm just going to equal Latin name of the element and the Latin. Okay. Metalloids, Latin name. And you see the benefit now of this is that I can fit everything on the screen. So I can just look at it, right? Let's go ahead and just show another merge real quick, just show what it would look like with this. Can't even do it, right? Yeah, there's no columns to merge on because with the only thing these have in common now is the index, right? So merge no longer works. It was originally working because they both had element in them. So here's what they look like. I think we can scroll over a little bit here. I don't know if there's a strong benefit to that. Oh, that's not what I meant to do.
85.
It was 85, thank you. Thought I would be able to scale there. Okay, yeah, very good. And then, so there they are. Sodium, natrium, very good. Okay. So I'm going to do one other thing right before I introduce the joins. Commonly, joins are taught with Venn diagrams. It was important to me to not just copy someone else's Venn diagram, and it was important to me to generate the Venn diagram in code that you could also use. The code on the next slide is similar to the Plotly example where I made a fairly complicated 3D plot, and I don't necessarily expect you to be able to do that tomorrow, right? But I didn't want to show you anything that I don't think you can make someday, right? So I'm going to introduce the Matplotlib Venn library. This is the way I like to make Venn diagrams. It does seem a little bit nicer, or a little bit less nice than a lot of the other libraries. To my knowledge, and you remember when I was introducing Matplotlib, I was like, oh, we got Plotly, we got Altair, we got GG. None of those things make Venn diagrams I like, right? So Matplotlib Venn is good enough. And this is what it looks like. You'll have to pip install this if you want to use it. All this nonsense here, those are the different overlapping parts of the Venn diagram, and I'm manually setting what all of their colors are. So this is extremely annoying to work with. Now, the default functionality of the Matplotlib Venn diagram is not that bad, but I don't know. It's not my favorite thing. So I'm going to be showing Venn diagrams, and I'm going to be showing example data frames, and I'm going to be showing example joins, and we're going to take a look at all of them. I do not think the pandas joins is the complete set of joins. These are a subset of the SQL joins, and we're just going to look at left, right, outer, and inner. We're also going to look at the cross join, but we're really not going to talk about it. I think Cartesian product is supposed to be capitalized. Yeah, that should be capitalized. Okay. So let's get cracking and let's get through this. So let's look at the first. We're going to look at, I think, the left index. Is that right? No, we're going to do a naive join. Okay. So let's go ahead and do. I'm going to break us out of full screen, and I'm going to type metalloids. We'll review what that is. I'm going to type join, and I'm going to type it on Latin name. What's going on here? So I joined the metalloids, or I joined Latin name onto metalloids. What happened? It added all of the columns in Latin name, but it didn't add any new elements. So it added columns, but not elements. So we keep all of the things that were currently in metalloids, and we add information to them. But we don't add new rows. So we add columns, not rows. That's a join. And that is the default join behavior. This happens to be identical to the left join, and I'm going to specify left join with a keyword argument. I'm going to specify how. and I'm going to say I want a left join. Okay? And that's going to be the same thing here. What does this look like? I take only the elements that are already in the metalloids. So it is this part of the Venn diagram. Okay? Let's go the other direction. Let's take Latin name dot join metalloids. I've never said the word metalloids this many times in my life. Here are all of the elements with Latin names. What do? We add no new elements to this, but we add a bit of additional information to antimony. Excuse me. Let's do a right join. Oop. I'm going to do a right join, and then I'm going to do a right join in the other direction. What's going on here? Now, our starting data frame, we're getting rid of all of its rows that aren't in the other side. So these are just symmetrical to each other. Changing left and right is the same as changing the order of the arguments, right? We only have the elements in the argument to the function, right? So these all have a Latin name. When I put metalloids inside join, these are all metalloids. Neither of these are necessarily quite what we're looking for, but I will point out, merge only gave me this thing in the middle already. So we're already doing a little bit better. And in fact, if we merged Latin names back into the main data frame now, this would work, because there's nothing in the Latin name data frame that isn't already in DF, our big data frame, this one, with all of the elements. This is the one I was kind of going for. Metalloids dot join outer. And this one's kind of cute. Because it doesn't really matter. You have the same information in both of these data frames, right? The only thing that changes is the order of the columns. But we have all of the elements from both of the data frames are in this big resultant data frame, no matter which way we combine it. And the only thing is Latin in this position in the middle, or is it on the end? That's the only thing that changes, right? So outer join was pretty much what we wanted earlier, right? And I think you can even do df.merge ad how equals outer. Does that work? And that gives us what we were originally looking for, right? So many of the types apply to merge as well as join, right? There's Wolfram. Okay. Oh, that's extremely wrong, actually. Do you see this? There's 2 tungstens in here now, because this has tungsten as index 118. I wonder if I spelled tungsten wrong. That's very interesting. Okay. The inner join is pretty interesting. I don't think this one's used that commonly. This is similar to the merge example. Latin name dot merge inner. So we only take the thing that is in both of the elements, right? Just the thing in the center. When do you want that? Well, if you can't have unpopulated columns, you have to take the inner join, right? I have never in my life seen a cross join, so I'm not even going to show you how to make it. This is all of the pairs. I don't know when you use this. Sometimes, I guess, right? If you have 2 data frames and you want to see all combinations of the 2 of them, sure. We're not usually combining elements, right? So you necessarily have to be combining something else. And now it is time for our exercise, which is great because I'm thirsty. So I was going to take a big gulp of water while you were working on this. This might seem like a really cool exercise to you or not. I'm not sure. This was my favorite of the exercises we've done so far. I'm really excited we've gotten to it. And it had to be after matplotlib, and it had to be after pandas. To the best of my knowledge, the periodic table was developed by Dmitry Mendeleev, who was a Russian. I usually make some effort to point out when people who are not necessarily Europeans are definitely the first people to invent things, right? Because I don't think a lot of times history has given credit, which I mean European history, to non-Europeans. It is, I think, up to Russians whether Russians are European or not, so I'm not going to make any claims about that, but Dmitry Mendeleev is not from France and not from Germany, and was the first person to study the periodic table. The way I think it was described to me, and I don't know if this is true, is that essentially Mendeleev had some flashcards and was laying them out like on a train on the way somewhere, and realized the layout of the periodic table of the elements. We can actually do the same thing. That's much easier for us because we don't have to have the original idea. So basically, the number of outer electrons and the numbers of layers of inner shells that can't bond form the rows and columns. We increase our number of protons across the rows and as we go down the columns, but we increase by one across, and then we increase in big blocks by going down columns. I don't really know how science works, but that's how it was understood to me. Separately, when you lay out the elements in this arrangement instead of linearly as a line from 1 to 118, this pattern emerges in a lot of different things, but the most interesting pattern to me was always electronegativity. Electronegativity is, I think, how likely something is to bond with another element. And so fluorine is extremely good at bonding with other elements. The classic example is the Nobel gases, which are the elements that have no valence electrons that want to bond, were famously thought to not exist in any chemical compounds. That was somewhat recently, I think like within the last 100 years, recent, found to be incorrect when xenon hexafluorine was discovered, which is a noble gas surrounded by fluorine elements, and the fluorine elements are so excited about binding with other elements that they can bind with an element that cannot bind. And they just sort of pull at each other directly through the element. It's very cool. It's a very interesting shape. You can take a look at it. So I found electronegativity very interesting because I was always interested in the noble gases. And fluorine is the only element that can bind with the noble gases. So here's your task. And this task is going to make more sense when I show you the product you're supposed to make at the end, but I'm going to describe it in words first. Plot the periodic table of the elements by plotting groups versus periods. Plot electronegativity using color. Confirm the claims of the chemistry text about electronegativity trends, which is what? Fluorine will be the most electronegative element, and values range down to cesium, francium, which are in another part of the periodic table, right? And annotate the location of fluorine, okay? I'm going to introduce one other thing to you that I think will be kind of nice. When I've been showing you the plots of the periodic table, the first row is at the top. When I was showing you plots of income tax, the lowest income tax was at the bottom, so you're going to need to change the direction of your axes. So here's the example of the taxation. Remember where it was going up? You probably don't want that with your periodic table, so there's two ways around this. You can just put a negative on, but that negative causes there to be negative signs that show up on this axis. You might or might not want that. You might just turn the axes off, right? But there's one other thing you can do. I don't remember what this, get current axes, right? You can just invert the y-axis, and you can use the same technique to invert the x-axis, right? So now our axes are upside down. We're growing down on the page, right? Which might be more natural. So I wanted to introduce that to you. Here's what the graphic should look like. You probably recognize this as the shape of the periodic table of the elements, the periods, and the groups. You could also call these rows and columns, right? Are labeled appropriately, and I have a color bar over here denoting electronegativity. We noted earlier that electronegativity is on a scale where fluorine is 4. That looks a lot like 4, and that looks a lot like 4, and that's where fluorine is on the periodic table. And I have also annotated fluorine. The code is in here, but you should generate this yourself. I'm going to take a little break, and you work on that, and you can take a break if you need to as well. Okay?
Sorry. chlorine
Mm-hmm.
is located on which one? Is it 17 or which one? 18?
I think it's 217.
270?
Let's see. It's probably like 7. That's argon.
It's atomic number 18. That's chlorine.
This is chlorine. Okay, so we need there we go. Period 2, group 17. Got it? Nice. Cool.
Is the air from the reds.
Yeah. Well done. Dang it, I didn't finish my toast. Okay, good job.
Just let me have a just bathroom break.
Oh yeah, okay. Cool, then I get to finish my toast.
오빤 강남스타일 강남스타일 낮에는 따사로운 인간적인 여자 커피 한 잔에 여유를 안
finishing stretch here. See, what month is it? It's after May 20th, right? I don't know what date it is. Doesn't matter. Cool. Just looking up conferences. These weekends are interesting because like my entire life warps around them until they happen. And there's like a bunch of things that have to happen in like the next 10 days when I get home. There's a lot of things I was like, oh, I'll deal with that when I get back. And it's like, will I? On to SciPy. Which, by golly, I've been saying SciPy for years. I didn't know if that was correct. You go straight to this website, and the very first thing they say is, please say SciP. My partner, who's a chemist, calls it Skippy.
Skippy.
Which I bet everyone hates that. It's basically, so NumPy is like a pretty big and heavyweight extension already, and adding vectors and arrays is a big deal. I think the original intention of NumPy was not that it would be the vector array library. It was originally going to be the thing that had pi and square root in it, right? And then everyone realized the only thing they really wanted to do was vectors, right? So NumPy sort of accidentally became vectors, and then there was still a need to have all of this other scientific computing stuff. So no problem, they said, okay, we'll make SciPy. But SciPy is really, it just keeps going further in the direction NumPy goes, and it gets bigger and it gets more diffuse and more specialized because that's the way science works, right? So to me, I don't view any difference between NumPy and SciPy at all. But it is noteworthy to think of this in terms of, well, I mean, really, Pandas was just like a thin layer of paint on top of NumPy as well. But like Pandas and SciPy feel very different, even though they both feel like the next thing after NumPy. So that's how I think of it. I believe SciPy is the most popular scientific computing platform in the world. I believe that SciPy inspired a number of scikits. The most popular one is scikit-learn, which again is something past SciPy. SciPy was getting too big, so they split scikit-learn off. And I believe scikit-learn is the most popular machine learning platform in the world. It's interesting that machine learning so aggressively came out of the sciences. I think it's often not perceived that way, right? But my understanding is like what the early machine learning people were all trying to do is they essentially had these spreadsheets and they had missing values in them, and they were trying to decide what to put in the missing values. Well, that's a very straightforward machine learning application, and it's much, much easier than doing things like inferring the future, right? But the climate models, we can think of them as machine learning, right? I think quite highly of SciPy because I perceive it to be extremely rigorous, and I think I've shown you this before. Some of these documents you can click through and you can see there's actual literal scientific citations for we do this for this reason because this paper got accepted at this conference by these reviewers, right? That really increases my confidence. I always get nervous when I'm using a library in any given language, really, and someone makes some claims about that their Gaussian denoising function is correct. And I was like, who are you to make this claim, right? And it's not that I doubt people innately. It's just like if I thought you were the world leading researcher in Gaussian denoising functions, I'd expect you to have a citation, right? So when you just put the citation there, it's like, great, I don't have to think about this anymore. Someone else has already determined that this is the right thing to do. When should we not use SciPy? I think there are two really clear notable cases here. You should not include SciPy unless you need it, and you should use NumPy if you can, is my impression. SciPy and scikit-learn together include complete statistics packages that statisticians don't seem to use. They use their other own thing called stats models. Stats models works just fine with SciPy. Stats models was probably the 11th library I would have taught. I was either going to teach that, Numba. I was going to teach two of Numba. What was the other one? SymPy and stats models. I didn't see a really compelling reason to teach stats models if I'm already teaching SciPy and scikit-learn, right? But some people really like stats models, so just be aware that stats models is out there. If you look up how to plot a trend line, someone might refer you to stats models, they might refer you to SciPy, and they might refer you to scikit-learn. All three of those libraries do that. I have legitimately never used SciPy for anything, because I always go from NumPy straight to scikit-learn without stopping at SciPy. I think SciPy has a bunch of like really interesting like signal processing stuff in it. And I kind of do signal processing, but I do it over discrete data, so I don't really use the types of libraries that SciPy has in it. But I think if you're like really into Doppler radar, you're going to use SciPy all the time. So maybe if you, when you graduate here, maybe you get a job in like telecommunications or electronics or something, where you're constantly reading signals coming in over the wire. That's SciPy to me, right? So this is a scientific computing course. We're going to do a bit of signal processing. We're going to do a bit of interpolation. That's the plan. I think the interpolation will be your homework, most likely is what it's looking like. Just so you know what I'm expecting programmatically here. I'm going to try and get back and write up what I expect will be a reasonable first homework, now that I know how far we've gotten this weekend in the next few days. But I'm probably going to ask you and the other student to both submit your .py files that are solutions to all of the exercises, so I'll probably ask for that by next Monday, which basically is to give you a week to get them all in an email, because they might be scattered across your computer and you might have to get home late or something like that. So I'm not going to expect those Monday morning tomorrow, but I think you have a lot of these Python files around. Hold on to those, and if you lose some of them, you know how to make them, so it won't take you too long to recreate them, I hope. Yeah, okay. So we're going to do a bit of signal processing. SciPy is huge. When things get this big, and I've mentioned, for example, I'm just teaching myself the Rust programming language, because what else do you do when you're a computer science professor, right? As things get bigger, NumPy doesn't really have this problem, where NumPy says, this is how you use NumPy, good luck, get out there, right? SciPy is too big, so it has a user guide, which is, hey, this is how some people use SciPy, or like, this is what we expect your questions to have. Then it has an API reference. The API reference describes basically all of the functions and methods in SciPy and their arguments and return values, right? So it is a reference text, it is an appendix, right? And then there's also the cookbook. I can't tell if the cookbook is official or maintained or up to date or not, but there were a few times I couldn't find the stuff I was looking for in the user guide and the API reference, which means I linked to the cookbook. Separately from all of this, there's a gazillion science professors across the world that are constantly publishing code written in SciPy that does cool stuff. So very frequently, if you want to know how to do something in SciPy, you can just say, hey, how do I do this in my computer? To Google or the search engine of your choice, and you're probably going to find some science teacher's website. This is in fact how we found the periodic table data we were looking at, right? I was just like, I'm sure some human has typed the periodic table into a CSV file, so I don't have to. And you go into the comments, and there's thousands of people saying, I was sure someone had typed this into a CSV file, so I didn't have to. We're going to install SciPy the same way we install everything else. How many pages do I have open over here? Okay. I still have Python open. We'll go ahead and restart that. Python 3-m space pip install Skippy. Got it. Do you have it?
Yeah.
Cool. Good job. Let's make sure we have it. Oops. Python 3 import numpy as np. It is in fact possible to use SciPy without np. Not particularly common. Import matplotlib.pyplot as plt. And then I'm just going to type import SciPy. I'm not going to import it as something. I've seen people import it as various things, oftentimes SCI, actually. And then I am going to print the version. SciPy.double_version. _ close paren. Enter. And I have a much more out-of-date version on this computer than I did back at home, which is fine. And if I could take a look at SciPy, it's, in the same place all my other ones are. Right next to NumPy. Right. Excuse me. Other installs. I wanted to do some signal processing, and really the thing you want to signal process is the values that come out of a radio telescope pointed at a distant galaxy. And I couldn't find that, so I thought I'd use SciGongnam Style from YouTube instead, right? So my apologies. I am not going to click that link because I'm currently streaming on YouTube, and I'll instantly become banned if I show you a YouTube video while I am streaming. So anyways, here's SciGongnam Style. It's right here. You can click on it. This is what it looks like. I have a note to myself reminding me not to click this, okay? We experienced this last term. We know what happens when I click links, okay? So that link is staying blue. Not to worry, I have some ingenious plans instead. So here's a lengthy explanation of what's going on. SciPy has the built-in ability to read some file types, but not others. And one of the file types it seems to be able to read is a .wav audio file. That stands for waveform audio file format. It looks like a relatively easy file format to read, and it looks like it's not very compressed. So I'm guessing it's used in science a lot because it probably doesn't introduce a lot of loss compared to something like an MP3, right? There's other things SciPy can't read. Famously, when I opened Pandas, I just read something directly from a URL. I can't do that in SciPy. So, what I'm going to do is I'm going to use a combination of other pieces of software. I'm going to take Psy's Gangnam Style off of YouTube, and I'm going to put it on my local device. And I think this process is going to work, so let's step through it. So I'm going to use YouTube, DLP, and FFmpeg, and I think that'll all work. I'm also going to use the VideoLAN VLC media player to play the WAV files. So let's see if I can get this to work. And I think this is going to be relatively involved. But this is part of the scientific computing process, so we're going to do it. And I'm going to go ahead and I'm probably going to want an additional tab here. Right? YouTube DLP. I don't have that. Now, I'm on Linux, so I'm just going to be able to install this at the command line, but that's not necessarily something we want to assume everyone can do. Wow, why is that going? I don't want that to pop up. Okay, there we go. So, you don't have to download any of these. I have gone through all of this work for you, and I believe this file will work. Let's see. I think there's no sound for the first 4 seconds. Oh, it's quite quiet.
오빤 강남스타일. 강남스타일.
Okay, there we go. So you can just go to this, and it looks like that is a link, and just download. So that is probably in downloads. There we go. And I'm guessing, I probably need VLC. I'm going to install VLC. Sudo apt install VLC bin. Password. Let's see if I can play this at command line or not. I know I can play it in Firefox. I already established that. Come on. Let's see. VLC work. VLC. Oh, I don't, or, maybe I can open. Okay, so VLC open Sci. That seems to not be working. Okay. Uninstall VLC bin. Remove. Let me go ahead and see. Okay, so VLC. Oh. Yeah, I want to remove it. Okay. I'm trying to get VLC working here. Okay, VLC, sudo snap install VLC. Surely this will work. But anyways, you have Gangnam Style, the .wav on your device. Did you play it in the browser or did you download it and then open it?
Download it.
Okay, so you were able to download it and open it. Good work. Okay, so I'm going to step you through the process that I used to get that file. I did Python 3m pip install YouTube DLP. Okay, and what'd that do? That installed the YouTube DLP package. What's the YouTube DLP package do? I don't know. I'm assuming the DL stands for download. I don't know what the P stands for. Perhaps it stands for package. YT stands for YouTube. When I do that, I have the YouTube DLP command. To this thing, I just give a URL. Hopefully we have a bunch of URLs around here. So I'm going to right-click this. I'm not going to left-click on it. Okay. All right. I'm going to right-click this, and I'm going to copy the link. Okay. YouTube DLP. I'm doing this in my downloads folder, by the way. I just want to point that out, so I'm not cluttering my my device. Okay. Go ahead and press enter. It's downloading a web page. We're all very proud of it. For some reason, it downloaded an iOS player. I don't know why it did that, but that's okay. And then we can see I have SciCom style. And I can't open that because I don't have the ability to open it yet, right? And I think that's because perhaps I can. Let's see, we can do. Let's see, VLC. Maybe VLC is not working. Okay, VLC. Okay, I have the VLC media player here. Cool. Oh, here it is. I forgot that it comes in quieter and then gets louder. I turned my sound all the way up because I was like, I can't hear it. So there we go. And I think I was able to just do that directly from command line, right? Yeah, okay. So I'm able to open SciCom, okay? And I'm probably able to open just the WAV file as well. And remember, we're pretending this is radio telescope data from a different galaxy, right? It just so happens to be the 9th most watched video on YouTube, okay? So that was YouTube DLP. On Windows, I think you will also need FFmpeg, and I might as well. And so the reason for this is because it wasn't that hard to get the YouTube video locally on my device, but I also need to do a file format change, right? I need to take that video data and I need to take the audio off of it. So how am I going to do that? Well, I can just use this YouTube DLP command, which specifies that I want it in an audio format, WAV, and that I want to get rid of the video. I'm going to copy paste. No, I'm not. I'm going to type it to make sure it works. YouTube DLP X. That means, I think, remove video. I'm not sure. I just read the documentation. Format WAV. I'm going to paste the URL. Very good. I am going to say -o. I'm going to say sci. We'll say sci2.wav because I want two of these. Okay. Oh, there's no auto format, so we're going to say audio format. And here's the issue. The ability to translate these files is not found, so I'm going to need to install that somewhere else as well. And so there's two places to do this. First of all, I used VLC. You don't have to use VLC. That's what I used. This is one way you can get the WAV file, right? Wait, no, I'm missing something. Right, okay. So here is FFmpeg. I'm guessing you're going to get this from this download page, and I'm guessing I'm going to get it from sudo apt install FFmpeg.
So to download this link, I have to install FFmpeg?
Yes. Or you can get the video, but you can't get just the audio. Also, I'm a little bit worried I'm teaching you how to steal music from the internet, but so don't think that's what I'm doing. Okay, so I installed FFmpeg. Use this responsibly. Okay. And then I have sci2.wav. Let's see if this sounds right. Okay. I think we did it. And I'm just going to remove all that stuff from my downloads file because I don't need it anymore. Okay. So that's how I got all these files. I wanted to just sort of show you how I did that, step you through the process. Generally speaking, in scientific computing, if you try something or look up how to do something, you just follow the error messages and you're able to sort of procedurally overcome one obstacle at a time. And the same thing will be true of the Doppler radio telescope data if you use that. Okay. So I used all of that through the command line. Wow, that is a really, why is that so long? That's very frustrating. Okay. I really would have expected there to be a line break there. Okay, no problem. All right, now we're going to skippy.io. You got the wave file?
I'm still downloading the FFM.
Okay, cool.
this file?
I didn't, but if I reopened my terminal, then usually it worked. Did you close and open your terminal in between downloading it?
No. I was PowerShell.
Yeah, or PowerShell. Yeah, just make a new one and see if it works there. Or yeah, let me pull up the command again. Shoot, which one was it? This thing.
Okay. No, still gives me there.
All right.
YTDLP is not recognized.
Oh, YTDLP is not recognized?
How did you install it?
Can you, let's see, where do I have a good window I can type this?
Wow, no, I got it. I use Python instead of Python 3.
Okay, yep.
That's fine. Nope, still there.
So you have the YTDLP command?
Yeah, I think it's something.
Do you have the ffmpeg command?
It's showing me to change the path of the file.
Which file?
The YTDL.
Okay. Good job.
Did you add Python 3 before YTDLP while downloading the audio file?
No, I just did YTDLP. So I do this.
I had to add Python 3.
Python 3 YTDLP.
Yeah, and then the whole link thing.
Yeah, I'm sure that's just the you
Because
having
I
two
think
installs
you are
on
in
your
the
printer.
downloads.
Yep.
installed YTDLP?
Yes, YTDLP is installed.
Okay. Yeah. Okay.
Now it says there.
Yeah.
When I tried, I closed the server.
Yeah.
But
Okay. Well, why don't you try Python 3 -m space pip space install. I'll see what it says. Space YT-DLP.
I'm
Okay. don't you try Python 3 space dash M space YTDLP, YT dash DLP. No module named YTDLP. Okay. Let's see. Can you copy paste that file location where it starts with C users and ends with site packages? Or the one that says where YTDLP is. Go up 2 lines. Not that one. The one for YTDLP. You see YTDLP, and so it says where YTDLP is. Okay.
Did you?
Just the name of the path, so starting at C and ending at site packages. And why don't you open just File Explorer and we'll navigate in there. So you have that open. Just click on the address bar and just copy paste it. Okay. So let's click through here and we'll follow the path. So the next thing was, I don't know what you copied.
Software
Yeah.
components.
There we go. And what's the next thing? Go check. Looks like local cached. But check, see which one it is. Look back at the command line. So it said local packages, local cache, local packages, Python 3.11. Local cache, local packages, Python 3.11. Site packages. And then there's supposed to be a YTDLP in here somewhere. There it is.
Just to find
I don't know which one we're supposed to look at. Good, go ahead and check that one. Okay. Oh, that's what it is. I wonder if you can import YTDLP. Scroll up to the top of this window. Let's see. Installer, dependencies, downloader, extractor. Why don't you just click on downloader and see if there's anything in there? Yeah, nothing really there. Okay, and then try the other one that was called YTDLP. So I'll go up one more. Yeah, I don't know what that is. Okay, dang, wish my Windows device with me. I'm gonna try something. And that is gonna be import YTDLP. Back in Python, can you import YTDLP?
installation. Oh, you can try ytdlp.exe if you want. think this link is the best guide I found that might help your problems if you want to look at it. And I think, what did I search to get that? YouTube DLP Windows. And I took the Reddit link, not the first thing. Good job. Well done.
It was the location for the. It was the location via TDLP. Python
Okay.
installed it on the wrong location, so I
Okay.
had to change the whole path.
Cool. Well done.
It took a lot of time.
All right. Let me get my ducks back in a row. Okay. So we're right here. And now at this point in time, I should realize that this single command would have let you got sci.wave from my device. But I think it's good that you learned how to do some file processing. So we'll mess around with, geez, where am I? Okay. Let's do a little bit of work with SciPy, and then we'll head to Atlanta, because we're running out of minutes here. Jeez. Okay, that goes over there. This goes over here. No. What? I can't get the windows where I want. There we go. Okay. Complaining about the windows on Linux is... There's an obvious solution to the problem of not liking how it's doing Windows. Okay. Cool. Can I type clear here? No, okay. We'll just empty this out. So, cool. I'm going to make sure I have all the things I want to here. Import numpy as np. Import pandas as pd. I'm going to import os. And I'm going to say os.system. I think it was in downloads. I'm going to say ls downloads. Oh, I lost the file. That's okay. I can get it again if I need to. Well, actually, let's go back. os.system. Curl. Did I get it? That might not have worked. Okay, I got star.wave. It's of size 0, which is a little bit suspicious, but we'll deal with that when the time comes if we need to. Very good. Okay, so let's do some SciPy. To load a wave file into SciPy, it is a simple matter. We're going to use the Python interface. Versus NumPy, as a rule, we're going to load in parts of SciPy at a time. This is very similar to matplotlib. We didn't ever import matplotlib. We imported matplotlib.pyplot as PLT. And we can sort of do the same thing with SciPy. So a good example is we're going to use scipy.io. So I'm going to import SciPy. I'm going to use scipy.io.wavefile.read. Oh, yeah, I spelled wavefile wrong because I'm used to putting the E in there. And so that is a function, right? And so I'm going to be able to use that function. Let me re-download this wave file first. I think I just clicked this, right? And then it downloads. Save file. Okay. And that is in downloads. Okay. os.system ls downloads. There it is. Okay. And I'm actually going to move that to being where I'm currently working. Move downloads /sci.wave. And I'm just going to tell it to move it to the local directory using a dot. Then I'm going to ls locally. And there it is, sci.wave. Easier to see it if I ask for the .wave files. Okay, so there it is. Let's go back forward a little bit. Let us do, and so I'm saying rate comma data here, and I'm just going to type that in first, and then we'll talk about why we do that. Equals scipy.io.wavefile.read sci.wave. and we got some rate, and we've got some data. There's going to be a lot of data, okay? This may look odd, and so we should talk about this a little bit. In SciPy, it's much more common to use multiple return. We have maybe had multiple return floating around the periphery here a few times. It's used a lot in machine learning. But it's not completely unreasonable to have an example of multiple return. And one example is we can have the function that returns the roots of some values, right? So I'm going to define roots of x. I'm going to calculate one of the roots, which is the np.square root of x. That's going to give me the positive root, but we also have the negative roots. So we're going to return root and negative root. So if I compute the roots of 25, I should get -5 and 5 back. And why is that? Because -5 squared is 25, and because 5 squared is 25. So this is a reasonable way to return values, right? And this will be also much more common when we do equation solvers that might return one or multiple solutions, right? Now, that passed this back as something that we might be able to recognize as a tuple. That's a tuple. But we can also unpack tuples, right? And so what unpacking means is it means we provide an argument for each one of the elements of the tuple. So I have a negative result, I have a positive result, and I'm going to set the negative and positive result equal to the roots of x, right? Oops. Of 25, I can see the negative, I can see the positive, I can see that the negative squared is 25, and I can see that the positive squared is 25, right? So I'm just doing the same thing here. This is not, and I think it is much less complicated when we're not doing this to a wave file. When we're just doing it to a number, hopefully this makes a little bit of sense. But that's the same thing going on here. When I read the wave file, I'm going to get back a rate, and the rate is just a number. It's just, that thing is as much just a number as any number can be, right? And then we're also going to get back the data, and the data is a NumPy ND array. SciPy doesn't really do the same having its own array type, like Pandas has data frames, NumPy has ND arrays. SciPy just uses the NumPy ND array. It's just an extension of NumPy. So we have that. The only real difference between lists and tuples is that you're not allowed to change the values of tuples. That doesn't really affect anything. I am going to show you a little bit of error handling here real quick. So let's make a tuple t. It's going to be 1 and 2, which are my two favorite numbers in order. Now, if I had a list that was 1 and 2, I could update one of my favorite numbers to be 3. That would be allowed. I am not allowed to update one of my favorite numbers in the tuple to be 3. That's not allowed. But so far in this class, I've only shown you code that actually runs, which isn't always good because sometimes you want to show code that doesn't work. So one way to do that is with a try except clause. So I can try to make one of my favorite numbers 3. And if it doesn't work, I can type except, and I can perhaps print a note to myself that says, "What are you doing, you silly goose?" Which is what all of my error messages say in all of the code I write. My code calls me a silly goose quite a lot. Sometimes it says, "Are you going honk honk because you're a silly goose?" That's another one it asks quite often. I also refer to my cat as a silly goose, so we have a lot of silly geese running around my apartment. But anyways, so this is an example of how we can write code that doesn't work. And then if it does work, we simply don't get called a silly goose. Oh, it just worked. I'm not a silly goose this time. So if you're going to write code that might explode, you can put it in a try except clause. Why do we introduce try except right now? Well, I kind of just showed the example. I just attempted to download sci.wave and it didn't work. Fortunately, I checked that it didn't work because when I was writing these slides, I spent about an hour trying to figure out why SciPy wasn't working when in fact I was trying to read a blank file. So maybe I should have checked to make sure the file was blank. And so that's the reason try except is in here. When you start downloading things from the internet and trying to open them in SciPy, you should first, perhaps open them in VLC Media Player and make sure there's actually a sound file there. Right? Make sure you actually have some data to work with. There's a variety of different sources of nuclear data that I hoped to use this term, and Python couldn't deal with any of them easily. Right? So I had to use try except, and I tried to find little snippets of data that weren't too nasty to work with. So This is the exact error that I just actually had today while I was trying to help you. But now we can look at the data. So let's look at the data. Let's look at the first 10 of the data. Should it be surprising to us that all of those are zeros? I'm going to make the claim no. Because when we listened to the media file, we noticed that it was initially silent. And then it got louder over time. I'm guessing that rate is the number of sounds per second, which means that I expect there's going to be 200,000 or so zeros at the beginning of this file, because I think there's going to be no sound for several seconds, and there's going to be 4,800 sounds per second. So I think there's going to be 48 times 4 no sounds, and I'm guessing that's what the zero is. That's my theory. But let's take a look at the plot and see what this looks like. So I just plotted this thing. Do I have matplotlib? Yeah. This is going to take a while. This is a big file. My computer might not have enough sauce to deal with this. The file is about 4 minutes long. There is 48,000 data points per second. There's actually 2 because it's a stereo file. There's 100,000 data points per second. In 4 minutes, there are 240 seconds. So there are 240 times 100,000 data points on here. That is 24 million data points that have to be processed. So if this processes 1 million data points per second, it will still take 2.5 seconds to show up on my screen. That makes sense, right?
That makes sense.
Yeah. So this is what the sound file looks like. Quite a few seconds off, and then there's a few times the sound cuts real low. See? And I think this is the, because we have the music video version, this is not the same probably as the official release, right? So there's like a credits. So this is, it tapers out into the credits, and then there's a credits sequence, right? Which is quieter. Right? And we also see, as I predicted, I mentioned when I turned my sound on, I noticed it got louder after a while, and we do see this volume jump right here, right? And then it's a consistent volume all the way through. So this looks to me to be very well mixed, which is interesting. It would be interesting to look at like songs on Bandcamp or something and see if they have the same level of professional mixing. You may have noticed that that took an extremely long time to render. We can make it render 100 times faster by taking a slice. And that is probably 100 times faster. And we get much of the same information, right? So this is one of the, ooh, no, it's still slow. It's still a lot of information, right? So this is a little more ragged. But you see we can go quite a bit faster by only looking at every 100th value, or perhaps every 10,000th value. And this will be much quicker, right? But now we're losing quite a bit of information. It's hard to tell that this is the same consistent value because we happen to only be sampling loud in a few places, right? But I think this probably looks like an audio file to us, right? Yeah. So this looks like a noise file, right? So let's go back and look at the rate. Oh, do we need to leave? We have to leave right now, don't we? Okay, it's 12:03. Any closing thoughts?
No, right now.
Okay.
No, thank you.
Yeah. My hope is that you'll be able to just click through all this stuff and understand it now that you have the downloads. This would be really hard, and some of this stuff is better to demonstrate at home. But let's see. Where was it? Right. I don't even know if I have stereo speakers on here, but this happens to only play through one of the 2 speakers. I don't know. Like to me, it sounds like it's coming from this side, and this one sounds like it's going to come from this side, probably. Can you tell? Maybe you can tell on your device, or if you've got headphones on later or something like that. So that's the real takeaway, and then I try and make some loops. So that's all that's going on here. I recommend when you're working on this on your own, just skip over stats. I just did that because I felt like I had to. But I am going to encourage you to do this exercise. probably for next Monday. All right, let's pack up and get to Atlanta and not miss our flights, which we're unlikely to miss, but let's not miss them. Let's see. Okay.